Come on, anybody. So you need to tell
So
me how
the
you have drawn. Yeah, please go ahead.
first we plotted
So I
the Gaussian distribution, which was the
just
hello.
just for the sake of video, I will repeat the question. So my question is how you have drawn a likelihood function. Yeah.
Okay, so first we plotted the Gaussian distribution, which was which was the probability of using that function one upon that function. So now for the mean you told for plotting mean is equals to 5 and variance is equals to 1. Now for likelihood
Mm-hmm.
function, mean is equals to 0. What was the probability that the probability of lying of 0 in that function, that was plotted on the same graph, and basically the probability was plotted, and for the same values, let's say 0 to 10 for the same samples.
Hmm. Anybody? Okay, fine, fine, cool. So what exactly I was what exactly I was like asking in low likelihood function, just for the quick recap. So what you need to be done there, that I had already asked you that there's a mean, and mean was somewhere, let's say at 5, and the variance was 1. So this was kind of a density plot that you had. Now you need to pick only 10 random samples. So there is a function in Python where you can pick random samples. So it was like 10 random samples. Then when you picked it, x1 to x10, right? So randomly you will pick some 10 samples. When those 10 samples are with you, then you just plot a likelihood function. Likelihood function where the variable is what? Variable is a mean, right? So you will change a mean and just uh, plot the total likelihood probability. So let's say the first you take mean equal to 0, then you may take the mean 0.1, then you take the mean 0.2, and you will vary this mean from 0 to 10, right? And when you plot the probability for every mean, then it will be some having a peak at 5, right? It will say that the log likelihood function have a highest probability at 5. So is anybody in the class have the same graph like what I'm discussing right now, or you are having some other ideas about this? So you need to vary a mean from 0 to 10, and there was how you can do that. You can just take a linear space division, and you just take mean from 0, 0.1, 0.2, 0.3, 0.4. Likewise, you could have taken 1,000 means from 0 to 10 with equal interval, and for every mean you had to plot a likelihood function, right? Has anybody done that, or like you have done on your own differently? Has anybody done that same way? Am I audible first? Like whether I'm connected to you guys?
Yes, sir.
Yes, sir.
Okay, so fine. So Vedant, have you done that same way, like, or you have done the same differently? The plotting of likelihood function for a mean from between 0 to 10 in a different way. So I hope that that different way is not what makes you understand the likelihood function. So I will soon up the code, and by the evening you will just go through that code and just get a feel of it, right? Okay, for today lecture, I will just try to repeat the things. You just understand it for today, and if something is that what you didn't get in previous lecture, let it be clear here, and then you redo the same exercise. So I was saying that for maximum likelihood, first we need to understand the likelihood, right? So in likelihood, I said that just take the some Gaussian and you can draw some 10 random samples. So for drawing 10 random samples, there are functions in Python. You can just take 10 samples out of it and it randomly comes, right? Based on the density. So because the density is very high here in this region, so the probability is high that the points will come from this region. Mostly points will come from this region. And because the density is less in this region, so there will be a less probability that the point will come from this region. So let's say we have drawn some 10 samples out of it, and these 10 samples are shown in these black dots, right? These 10 samples are shown in the black dots. Now, based on these black dots, you need to find out what is your actual mean and variance, right? So the probability of Gaussian distribution is this, right? And you don't know what is your actual mean, right? So as I said, you need to vary your mean from 0 to 10. So assume that mean is a variable here, right? So mean is a variable here. So mean can vary from 0 to 10. So if I say mean is a variable, so right now I am just seeing every other thing as a constant. So first you give this x to this formula. When you give this x to a formula, and you just calculate some there's some form, you will get some form, then you give mean point 1 here, right? You give point 1 here, then you give mean point 2, then give mean point 3, mean give point 4. So you will get different probabilities for different mean, right? So here mean is a variable, as I said. So you have a different probability for a different mean. So likewise, you calculate the probability for every x, right? You will calculate the probability for every x. So then you have probability p1 for x1, then you have probability p2 for x2, probability p10 for x10, right? So you had 10 x samples, then you calculate 10 probabilities and you multiply these probabilities. But still, you remember the only thing that is missing is mean here. So you take mean one by one from 0 to 10 and put in this formula. Whatever the values will come to you, you plot into this y-axis, right? So this is a y-axis here. So when you take mean 0.1, so for this P1 will have some value, P2 will have some value, until P10 will have some value. Multiply them, you will get some number. You plot that number somewhere here. Then you take mean point 1, then you get other number, mean point 2, point 3, and likewise when you go till 9.9 and then 10, there will be some this kind of curves you will see, and you see that it will have peak somewhere, and that peak wherever it will have, you just need to give that parameter to me back to me and say this is the mean which is giving the highest value for this data set, right? Is this clear to you guys?
Yes, sir.
So exactly this is what I want you to plot it, right? This is exactly what I want you to plot it. If you have done something else, I insist, I urge you to just redo the exercise so that you can get a feel of it, right? So here the only these product terms P1 to P10 is a likelihood function, and where only mean is not known to me, I try every possible combination for every mean between 0 to 10 and get my values, and then I will find it out, okay, at some particular mean mu, it is giving a highest peak, so that is a maximum likelihood estimation. So this is a maximum likelihood estimation for me, right? And based on this, you always return me that mean which will give me the highest value of this likelihood. This is known as maximum likelihood estimation. So for just to make me sure that you understand it, can you quickly write yes or no in chat box? Right. Okay, fine, good, very good, very nice, very nice, very good. Okay. So I really hope that this will give you the intuition of likelihood And please redo your exercise and plot those things to plot these things using MATLAB, and then let me know. So I will go and get it. Okay. Okay. So this is what we have done. Then I said that here there is a small catch, mathematical catch. When you multiply these probabilities, you may get a very small number, right? To handle that situation, what you do, you just take the log of this product, because it is a monotonically increasing function, or then taking a log and finding out a maximum will not give you the different result. So it means it is having the same effect whether you take a log and then get the maximum estimation, or without taking a log and then take a maximum estimation, you will get the same result. So, but taking a log will have an advantage that it will not underflow the things. Why things will underflow? Because if you multiply so many small numbers, then a small number will result into a further small number, and your computer may not be capable of getting or putting that small number into the memory. It can underflow. So just to overcome that situation, you take a log of this product, then this product will convert into a sum. So it will be log P1 plus log P2 plus log Ptn. So that's why what we do, we just take a log of the probability likelihood function, and it will give me this result, right? It will give me this result. So analytically, so there is a difference, guys, here. So what I have just done here, it is geometrically I need to plot for every mean, right? But analytically, if you ask me, what is this value of mean? Analytically means mathematicals, you have to do some manipulation in algebraic terms, and then you will tell me what is the terms here, right? So analytically, that you have to give me the mean here. So then in analytical term, what you can do, you just need to take this function as it is and need to maximize it. You need to maximize it, right? So are you getting the feel, Pravalika? Are you there? Like, Pravalika, are you there? So what I just have said, there is a two things. One is geometrically you had plot the likelihood function. The second I said that you don't need to calculate for every mean the value and then plot it and then maximize it. Analytically, you can do it in one shot. So analytically, what you can do, just write this function in terms of mu, and then take a differentiation with respect to mu. When you take the differentiation with respect to mu, what will you get? You will directly get this function, this value. So it means if you maximize a log likelihood function with respect to mu, it is nothing but a sample mean. If you maximize with respect to variance, it is nothing. Hello? Yeah? Uh, Personal Amazon. Just a minute, I will call back. So this is nothing but analytically, if you want to find out what is your mean, which will increase your function, then you don't need to plot for every mean and then maximize it and see it by your eyes geometrically. No, what you can do, you just take all samples, find it out the average mean, and that average mean will be the estimation of your maximum likelihood estimation. It means this is the same mean, this will be the same value, which will increase your function somewhere here, right? So this mean is nothing but the same mean. So it is an analytical solution. So first I told you geometrically how to see for every mean, and then I told you you don't need to vary for every mean, because there could be infinite means, right? You cannot do everything. So analytically, you just try to find out what is that mean which can maximize your likelihood function, right? So now this is a sample mean. And similarly, what is that variance which can maximize your likelihood function? You are taking a derivative, and this is that sample variance. Fine. Then I told you that this mean and variance, right, which we got using maximum likelihood estimation, this mean and variance may be biased. May be biased how? For an example, this is a case where I have a true distribution which is shown in green, right? So I draw two samples out of it. And when I draw two samples out of it and I calculate the mean and variance using this data set. So the mean from this data set is this and variance is this, right? Similarly, I draw another data set of 2 points. Using these 2 points here, I take a mean and sample variance. So sample variance is this and mean is that, right? Similarly, I taking a third data set from the two distribution green one. And this third data set is these 2 points. I take a mean from here and then take a sample variance, sample mean and sample variance. So in all three data sets, I have calculated sample mean and sample variance. If I take expectation of a sample mean over all three data set, I will get a true mean, right? But if I calculate a sample variance, I will get the same variance, right? Because let's say this is 2, this is also 2, and this is also 2. When I take an average, I will get a 2 only. But here you can see that I am underestimating my variance. So here variance using maximum likelihood estimation is underestimated, but the mean which I have calculated using maximum likelihood estimation is a true estimation. So the example what it shows is maximum likelihood always not give you a perfect result. Sometimes it underestimate the things and it will result in a very bad prediction, right? So to overcome this unbiased thing, sometimes you need to manage or sometimes you need to compensate it. And this is what I have just discussed in the last class, right? Any questions so far till here?
Yes, sir. When you say the variance is underestimated, it means the value is lesser than expected.
Right, exactly.
Okay, thank you, sir.
Okay. Anybody else have any question here? So it is not always that I can get less values or underestimated values. I can get overestimated values also. For an example, I had discussed a case last time when I said that if you toss a coin and you get a head, what do you think using maximum likelihood estimation, the next will be head. Then you said that it is a probability one that every time you get a head. It is overestimation, right? It's not an underestimation. Fine.
Yes, sir.
Okay, if this is clear to you, let's go to the next thing. Then I said that, okay, so from here onwards, I want your complete attentions because I'm going to take my linear regression case again. So guys, can you give me a just break because I'm getting some call. So just 2 minutes here, right? Okay, so hello, yeah, I think it's a wrong number. Yeah. So this is like what I want your proper attention on it. So uh, we have just discussed linear regression intuitively, and now I am trying to give you a probabilistic modeling. So this is a first model, probabilistic model, which you are going to get now. So I want your full attention on it. If you have any problem in understanding anything, you can stop me. I am ready to discuss with you here. And from then onwards, I will be taking you granted that you are understanding this model, right? So let's start with this linear regression thing. So I told you, if you remember, in linear regression, we had an idea that there was some data points we have generated. Those data points were having some random noise added to it, and points were generated from some function. Let's say that function could be sinusoidal or that function could be a line, right? So this is what we had an assumption. So that there could be a line, and that line we have generated some samples from it, and then we added noise to it, and then we forgot that the true distribution, true function was a line or a sinusoidal, right? This is what our assumption. Here, what we say that rather than just fitting it directly, we will introduce some probabilistic modeling here. And for every x, what we will say that we will not get one value of y, we will get a distribution of y here, right? So we'll say that I get maximally this value for this x, right? Let's say I just to name it, it is x1. So I will get y1 here with a maximum probability, and with lesser probability, I am getting this point, which is deviated from y1 normally, right? As a Gaussian distribution. So I will say that maximally, I will get the point which is at y1. And once I walk away, either in positive or negative direction from y1, the probability of getting the point from y1 is less. And how less it is? It is according to the normal density or Gaussian density. For this point, if I want to predict some point here, x2, then you give me a probability distribution over here, and it says the maximum probability for y2 is this. And if you walk away from this y2, the probability will be following the Gaussian distribution, right? So this is what my modeling is. At first, I had a one target variable for one input variable. So for every x, I was having only one variable, t. So just to bring the same notations from the previous slide. So rather than using y there, I had used t. So for every x before I had used, there was one t. Now I am assuming there could be multiple t's, but those infinite t's have a distribution over them, and I always pick the maximum probability out of it. So rather than saying I can get for every x, I will get only one t, I will get there will be lot of t's. There could be lot of t's, and every t is possible for this x. But there is a distribution over these t's. And out of this distribution, I will take the maximum value, maximum probability t here, which is at the mean, right? Any question on this assumption? Any question on this assumption?
No, sir.
Okay, anybody else? Akash, are you clear with this?
Yes, sir.
Okay. So if this is done to you, then how you will write it? So you will say, let's say you want to predict for some particular x, right? You want to predict for some particular x, and you know there is an underlying function for it. It may be a sinusoidal or it may be a line. Just for simplicity, I will take it a line. So once you plot a line, right? So for yxwt is a line, let's say. So this is a line. You want to predict for this x. So this x is, let's say, this x. Then you say that this is a mean. This is a mean. So if you plug the value of x in the equation of a line, you will get this value, right? So you are saying this is a mean. Then you say this is a variance, beta inverse. So where I'm writing just in beta is nothing but a beta. You can write it like this. Beta is equals to 1 upon variance, right? So it is just another way of writing variance, not to confuse you. So just take it as a variance. Beta is nothing but an inverse of a variance. So now we are saying that if you want to write it into if you want to predict a value of a target for some particular x, right? For some particular x, then what you will do, you just find out a mean. How you will find out a mean? Because you know there is an underlying function. For that function, you plug your value of x into that function. It will give you the value of a line. Then you just consider that value of line as a mean. And then you say that there is a variance using by beta. Then you will get a density plot. Once you get a density plot, you pick any random number from it using Gaussian distribution. So if you take any random number, the probability is very high that you will going to pick a mean, but not absolute mean. It could be some up away from the mean with some probability, but it is very sure. The number which you're going to get very far away from the mean is having a very less probability. But you are not denying the fact that I will never generate this number. You say that I can generate this number, but very, very less probability. And the higher probability is still this number because it is at the mean, and mean is having a highest probability, right? So if somebody asks you to generate a number from this symbolic notation, then I hope that you can easily read this thing, right? You can easily read this equation. Any problem?
No, sir.
You can read this equation now, you know?
Yes, sir.
So because it is a, so the now your can anybody tell me, I'm really eager to listen get this answer from you. Can anybody tell me if this is a problem statement for you, then what is exactly I'm looking? So this is a problem statement. I am looking, I have just constructed my problem such a way that I want to fit my data. So what is exactly I am looking into this equation? What is exactly I'm looking into this equation? Given my data, that data is provided to me, what exactly I'm looking now? Just to predict something for unknown X. So this is a machine learning problem. You have given me a data. Once you given me a data, then I have to, let's say this is a problem construct. So I can predict my value of T for a given X. So I need to do something. So what is the target? What is the solution for my this problem? What should I, what is my quest? What I'm looking for? Can anybody tell me in this construct?
We're looking for a function to map most of the data.
The most probable function, sir.
Most probable function, right? So can you name that most probable function here?
Um,
I have written this name of a function in this equation itself.
Sir, yx comma w.
Sorry, I couldn't hear you.
Yx comma w.
Exactly, exactly. Very good, very good. So here, I never knew what is my true function, right? And I'm estimating it. In effort of estimating my true function, you know the function is defined by what? The function is defined by what? Can anybody else try for this answer? Now my quest is to find out my y, true function. But true function can be defined by what? True function is a parameterized version, right? So I need to find out a parameter for the true function. What is a parameter for the true function?
W.
Very good, very good. So in effort of getting my y, I need to find out at one further level in my quest or in search. I need to find out w exactly. So this is my w, which inherently define my y, and once I get a y, I know there is a construct of Gaussian distribution over there. Once you give me y, I always get me a t with some probability where beta is given to me. So beta can also be learned. So here w is fine, but the other parameter is also there, which you should not forget. This is what is your variance around your y, right? So I have said that it is a beta precision, which is an inverse of that, right? Variance. So here there are three. First, you wanted to know y, but just to know y, you need to know w, because w is defining y. It just who, for those who are not understanding it, it is like you not need to find a line, but you don't know what is a line. Then you need to find out a slope and intercept. What is slope and intercept? It is w. So first you need to find out a line. Just to find out a line, you need to find out intercept and slope, which is w. Once you get a line, then you find out, you need to pick a number from it. To pick a number from it, it is always defined by a variance around that line, right? As I said, it is a variance around a line. So that variance is given by beta. So beta is also a target for you. So you are looking for two things here, w and beta. Fine. Okay. Okay. So for Yogendra and Jitendra, those who have written likelihood function, just I want to connect a dot for you guys here is this. If you give me, if you ask me a probability of, so I will just redraw this function. So you please hold an attention here very carefully. You give me a data set, right? This was my data set. And I thought I thought that this data set was produced by some line, right? If this data set was produced by some line, then definitely I have a construct of my y is equals to this. So my function y is nothing but a mx plus c, right? Mx plus c. So I don't want to write that mx plus c. So I will just write into hyperplanar form. So it is w transpose x. I told you, right? Every line can be written into a hyperplane form. So it is, my line is nothing but w transpose x, right? Once you give me this general form of a equation, w transpose x, then you are asking me what is the probability of this point. What is the probability of this point? So to calculate the probability of this point, I will take this w as my mean, right? I will take this w as a mean, and you know the Gaussian distribution formula. So just for you, there is a constant, there is an exponent here, minus half x minus mu whole square upon variance, right? Can anybody tell me what is a mean here for me? For this example, what I am discussing right now, what is a mean here for me?
W.
No.
X.
Yeah. Anybody? You need to see this equation very carefully. What is the mean
X
here
is
for?
mean.
No, x is a data. Yes, Yogendra has said that wxy. So wxy is a mean in this, for this equation, right? But when I am taking a specific example here as a line, what is a mean? Wx comma y is a general function, right? But I am taking a specific example now. Can anybody tell me what is a mean?
The value of y at x equal to x naught.
No. My mean is nothing but a line itself, right? So rather than saying it is yx comma w, which is a general form of any function, I am specifically taking in this example is a line. And how I am defining a line here in this example?
W transpose X.
Exactly. This is W transpose X, right? This is a W transpose X. Once I freeze the form of my parameter equation function, I say that my line, my function is W transpose X. So rather than writing W X comma Y, which is a very general form of any function, I said that my function is fixed now. It is a line. So I said that it is W transpose X, right? So it is a W transpose X. And when I fix my mean, and you want to plug this mean somewhere here, it means you will write, rather than taking this, your mean is x minus w transpose x, right? W transpose x whole square, right? Can you see that your mean is changing for every x, right? For this x, this is your mean. For this x, this is your mean. And for this x, any x, like for this x, this is your mean, right? So the mean is keep on changing, right? It is not fixed, like as you have seen. So now I have put my mean, and do you remember? Do I know my mean in general?
No.
No, very good. When I don't know my mean, in that mean exactly I know w, right? I know x, but I don't know w. So as I said, I'm repeating these questions again and again just to make you clear. I don't need to just brush all these things so many times, but still I care that you should understand every aspect of it. So here w transpose x was a mean which you were looking for it. And if you just decompose this form in this w transpose x, x is still known, right? Because it's a data, and w is not known. So your ultimate aim is to find out a w. Okay, how I am going to collect it with a likelihood function. Any genius can tell me. Any genius in the class can tell me how this construct of what I'm putting it on right now on slide, how can I connect this thing to my likelihood function? So this is a probability. This is a probability of 1 point, right? This is a probability of 1 point. For given x1, for given x1, this is a probability, right? So you take, okay, I will just brush it and rewrite it again, just you can be very clear. So I have 10 points here, right? I have 10 points in my data set. I have already known that my functional form is a line here. So this is 1 point, this is, let's say, second point, and this is 3 points. So there are 3 points here. And these are the mean for first point, this is a mean for second point, and this is a mean for third point. So I will calculate the probability of a first point first. So this is the probability of a first point. So let's say constant e to the power minus half. My first point is what? X1, which you're going to put an exact value. Let x1 is 1, right? So x1 minus mean. This is W transpose x1. W transpose x1. And then my variance. Variance is nothing but an inverse. So it is, I can write beta here, right? So this is a probability for a first point, x1. What is the probability for second point? It is k e to the power, beta is fixed, right? It is not changing with x. So e to the power beta upon 2 x2 minus W transpose x2, right? This is a probability of a second point. Third point, k e to the power minus beta upon 2 x3 minus W transpose x3. How will I compose my likelihood function? Anybody? These are the 3 probabilities P1, P2, P3 corresponding to x1, x2, x3. How I'm going to get a probability likelihood function from this? Multiplying them, right? Yashdeep. Yeah, very good. By multiplying them. As I told you, that likelihood function is nothing but you are multiplying the probabilities. So you multiply these 3 probabilities, and this is your likelihood function. Analytically, you want to maximize them. So I will ask specific question. If analytically I want to maximize them, what is my variable here? Rahul Priyadarshi. What is a variable here? If I want to maximize this likelihood function analytically.
So X.
Boom. Anybody else? W. W is the X is known to me. You always give a data set to me. When you give a data set to me, anybody in the world who's data scientist or machine learning, every time data known to them, they don't know the parameters. So W is not known to you. So if analytically you want to maximize this function, what are the variables here? What are the variables? One is W, other variable is? One is W, other variable is? Very good. Very good. It is beta. Akash has said it is a beta. Jitendra has said it is a beta. So there are 2 variables here only. In which respect I want to maximize this likelihood function. The trick that I just told you, it is a product. What should I do to just make it so that it should not underflow? What should I do to that?
Take log.
Take a log of it. Very good. Very nice. When I take a log of it, boom, it is not okay. If I take a log of it, then obviously what will happen? Then you just expand this formula. I don't know. Hold on just a minute. I can't. So Once you take a log of it and you maximize it, you will get your desired answer. Okay. So I hope that I am just done with the today's class. So any questions before leaving it? So my request to you guys is, I want you to be, everybody want you to be pro in this machine learning thing, right? So you take this product form, take a log of it and maximize it, because you know the calculus, right? You know the calculus. Tomorrow in the beginning of the class, I will do this derivation again for you guys. But for today, I insist you to take this product form, right? Can you see this, which I am boxing every time? Can you see this thing?
Yes, sir.
So what you do, this is a product of the probability. This is a probability. If you expand this probability, you can see this probability this way, right? So you take the product of this function, you take a log of it, you will get some value. Then you maximize it with respect to W and beta, right?
Okay.
And whatever you will get, you just keep it with you. Tomorrow in the beginning of the class, I will show you and prove you that maximizing this product of the probabilities, that is likelihood function, is nothing but minimizing the sum of square function, which we have started before, right? Do you remember that in linear regression we were minimizing the sum of square error? Can you write yes or no for this?
Yes, sir.
Yeah, please. If you very good. So we were minimizing sum of square error when we were doing linear regression function. I will prove you tomorrow that minimizing the sum of square function and maximizing the log likelihood function is exactly the same thing. Oh, tomorrow is a holiday. I mean to say next class. Yeah. Thanks for reminding me. Thanks for reminding me. You're very good at picking the holidays, right? Oh, genius. So in next class, I will be just saying you that I will be proving you that minimizing the sum of square error is nothing but maximizing the log likelihood function. And I just can give you a guarantee as per my year of experience on machine learning that this is what all is. Constructing an error function is nothing but maximizing a likelihood. And if you take a negative of maximum of log likelihood is nothing but you are minimizing some error function, right? So we will talk on this more, right? So today your task is to take a log of it and take a derivative with respect to W and beta. Fine, if we don't have any question, please drop your attendance. Thank you very much.